Hello, my name is Wang Rongjian. I'm now studying high school in Beijing, RDFC ICC. In the paper I'll be presenting today is titled IMM-EKF based GPS-INS combined positioning method for drone. And in this paper, we basically combine GPS and INS and also proposed IMM-EKF method to track different motion models in order to achieve positioning with high accuracy and reliability. So first, let's come to a brief introduction of GPS and INS. These two are the most commonly used positioning system nowadays, and the integration of them is now widely applied in many fields like precision agriculture, traffic and transportation, and ocean development, and also military application and so on. And this really has a great beneficial effect on the economy and society. And the data shows that it has generated over $1.4 trillion since GPS was made available for private sector use in 1983. So then, the reason for combining GPS and INS is that they are actually complementary. And GPS can provide all-weather, high-accuracy position, and speed and time information, but the update frequency of satellite signals is low. And also, as we know, GPS works by several satellites working together to get the distance. So it's it's relatively susceptible to interference from the carrier movements and also external occlusion. But on the contrary, the INS system using the principle of inertia and can use its own inertial system for positioning. So it's not easy to be interfered. And but the thing is that due to its own inertial sensor accuracy and the calculation principle of the integral, the cumulative error of INS over time is very serious. So it causes its accuracy to decline greatly. So according to their own features of GPS and INS, and we can see they can actually beautifully compensate for each other's shortcomings and to achieve better positioning, accuracy, and reliability. So then comes to the GPS and INS integration status. Now there are loosely coupled one and tightly coupled mode. And the picture on the right side, those two pictures can show the differences between them. And for the loosely coupled one, it has advantages like it is simple in application, and since all the sensors are aiding each other, so the loosely coupled mode has a strong robustness, also with a short processing time. But the thing is that in some regions that GPS covers poor, then it's kind of impossible to provide the measurement update from GPS filter. And for the tightly coupled mode, it can be used in the urban areas, in some poor satellites cover areas like the urban area. But there's also a disadvantage that its increase in the state vector size can lead to a long processing time, so it's not efficient. And there are also other methods like uncoupled integration and ultra-tight integration, and they also have their own features as well. So then comes to the IMM interaction multiple model and EKF framework. So the interactive multiple model method can stably track different motion models obtain the weight of each model through a likelihood function of each model, and then feedback the calculated joint state distribution estimation and covariance to each filter model to improve its accuracy and robustness of fusion positioning. Anyway, it basically involves 4 steps. The first step is the model interaction as is shown. Just as the name of IMM framework suggested, there are multiple models. And so basically the possibility of each model will be obtained in this step. And this is achieved by calculating the predicted probability of other models and also mixing the initial state covariances. And after that, that is the filtering part. And these steps will apply the common filter. And the common filters can work pretty well in tracking continuously moving object to provide a more accurate position information. So then after the filtering part is the probability will be updated for each model. And let it be noted that in IMM framework, the model update can directly affect the effectiveness of the algorithm. So it's pretty important. And this step will calculate the similarity between the current model and the current movement of the moving object. And then the update of the probability for each of these model will be obtained. And then the last step is the estimation and covariance combination. So through the both states estimation value, covariance matrix and the estimation error, and measurement of the probability, then the comprehensive filtering result of the multiple model can be obtained in the end. And these steps may be not so clear, so I made a general flowchart here, and we can see there are multiple models, and then first is the interaction step. After that goes down, there are many common filters working independently. Then after that, the probability will be updated. It will go upward to the interaction part, then repeat this process. Then finally, we can get a more accurate estimation and covariance combination. So then, these are the different motion models in the framework in the paper. And when we're considering the movement model of drone, we assume it basically have 3 different types of motion, which is constant velocity, CV, constant acceleration, CA, and also constant turn, CT. And just as their name suggested, and it's easy to understand, in CV it's moving at constant velocity, in CA it's moving at constant acceleration, and in CT is turning in a constant velocity. And these things below are the state variable of drone, and we take X and Y position and the velocity into consider. We can see X, Y, and Vx, Vy, and also in CA model, we also take the acceleration into consider, of course. So this page are the specific stochastic metrics for each model. This is for CV, this is for CA, and the last one is for CT. And actually, the important point here is that these different metrics define exactly how the carrier will move in the different motions and can help to calculate a more accurate estimate position for the, if you remember, for the filtering part. So then we'll come to the simulation part, the computer simulation. And in order to verify the effectiveness of the method we propose in this paper, we simulate the movement of the carrier with MATLAB. The motion model of the carrier includes 3 models, just as we mentioned before, CV, CA, and CT, and the measurement noise is assumed to be 2. So then, that is the trajectory shown in this picture in X and Y direction. So after the simulation that show you the result, the final result, we can see from the mean error graph that the mean errors in X and Y directions are within 2 meters. And also on the right side, the root mean squared errors graph, RMSE, shows the velocity errors in X direction is large in the initial state. We can see it's pretty large at about 0 timings. And after that, but the velocity errors in X direction is generally smaller than the velocity error in Y direction. It is shown clearly in the graph. So that is the position error probability accumulation map. And it can be roughly seen from this that when the probability is 67%, the positioning error is, I think, about 0.9. So let me make a conclusion about that. This paper proposed an IMM-EKF fusion positioning method by dynamically tracking the motion model of the drone. And it considered the drone has different states when the constant velocity CV, constant acceleration CA, and also constant turn CT motion. And the transition matrix adjusts the carbon filter transition matrix in real time through the motion transition probability to achieve the high accuracy positioning in a complex environment for a long time. And finally, based on the method proposed in this paper, we made a computer simulation, and computer simulation of the drone motion trajectory, the average error of the position of the carrier in X and Y direction, and also accumulated distribution of probability of precision error or analysis. And the final result shows the velocity errors in X direction is large in the initial stage, but the velocity error in X direction is generally smaller than the velocity error in Y direction. And also the error of both are basically within 2 meters. So in the end, when the cumulative error probability is 67%, the bit value error of the navigation carrier is about 0.9 meters. Well, I think that is the end of my presentation. And thanks again for the conference to inviting me to share the paper. And thanks very much for your listening.